We've heard that nothing can travel faster than the speed of light, and that if it has mass, an object can never reach the speed of light. But what's the physical reason for that? We know that it's encapsulated in Einstein's equations and the Lorentz transformations, but what's physically going on? Well, it takes infinite energy to accelerate an object to the speed of light. But what's the reason for that? The reason for it is every object, believe it or not, is made up of waves, matter waves. And you're basically just a huge collection of trillions of different wavelengths all piled up together to make one big wave pulse. And when you accelerate, you can change the frequencies of these pulses and move forward at a faster rate. But it takes an infinite amount of energy to make this wave pulse that you're made of have a group velocity equal to speed of light. And that's the reason. A lot of people ask me, which interpretation of quantum mechanics do I think is valid? Let me just summarize a couple of them here really quick. There are many others. So there is the Copenhagen interpretation. That's the one accepted by standard physics. And basically what it says is that a particle could be described as a wave function. The wave function has all of the information about the system, from the possible positions that the particle can occupy, to the possible energies that the particle can have, to the possible momentums that the particle can have. And it can exist in a superposition of these until we make a measurement, at which point one of these possible values is actually measured. But then if we leave the system alone, it goes back into this superposition after a certain unspecified amount of time. Now, this is an incomplete interpretation of quantum mechanics, in my opinion, because the length of time specified for how long it takes the system to go back into the superposition is not explained. It's not explained why, when we make a measurement, one of the possible outcomes is chosen. And by the way, the possibility is random. It's like flipping dice. Hence the term, God doesn't play dice. That's why Einstein didn't like this interpretation of quantum mechanics. However, this interpretation of quantum mechanics perfectly explains the behavior of the atoms and the behavior of the electrons. So as far as making predictions for possible values, I think that the theory is perfect at making predictions. As far as explaining what's actually happening, like physically, why is this occurring? There's no explanation given. So that's why it's an incomplete description. Okay, what about many worlds? Many worlds says all the same things as the Copenhagen interpretation, except it goes one step further, and it says when you make a measurement, one of those possibilities is chosen, but there's nothing special about that choice. So all the other possibilities also get chosen in other universes, and everything splits apart into multiple universes every time a choice is made. I doubt this because it doesn't obey any kind of principle of energy conservation. However, as we've seen, energy conservation isn't as strong as we would have thought in classical physics. It can actually be violated in general relativity as well. However, I'm just ultimately skeptical. My end statement is this. I do think that quantum mechanics is incomplete in its description, and I do believe in the future, perhaps the near future, we will actually have a much better understanding of the physical mechanism that lies behind this wave function just choosing a value. And it might still be that it's random, but I think that we will have an explanation in the future at some point as to what's really happening. The Einstein field equations describe all the incredible effects of gravity as the bending of space and time. But there's a huge problem. While these equations work brilliantly and describe a whole host of incredibly experimentally verified effects such as gravitational lensing, black holes, and even dark energy, these equations, which describe the force of gravity as the bending of space and time by energy, have a huge hole in them. And the problem deals with the uncertainty principle. According to the Heisenberg uncertainty principle, the uncertainty in position times the uncertainty in momentum must always be greater than or equal to h bar over 2. This means that the position of an object is never certain, but that means that the gravitational effects caused by matter and energy bending space and time is fuzzy and not well defined because we can't precisely define where an object is. While common sense would dictate that the object is probably located in the vicinity of this uncertainty range, and the uncertainty range is tiny, to be precise, we need to understand how this interaction of gravitational effect caused by the bending of space and time manifests itself in this quantum mechanical uncertainty regime. This is one of the big problems that needs to be solved in order for us to have a unified theory of physics. This is sort of the quantum gravity problem in essence, because we have this uncertainty in position and momentum, but with an uncertainty in position, we have an uncertainty in gravitational bending. So we need to understand, how does this manifest itself, and how do these two different aspects of nature interplay and relate to one another? All right, let's answer some questions. A viewer asks, why do electrons exist as a probabilistic wave function, but protons and neutrons not? What accounts for this difference? Actually, everything exists as a probabilistic wave function, even you, but there's a reason we can't observe it in larger objects. Even it's harder to observe with protons and neutrons. The equation for the matter wave is behind me. Notice that the momentum is in the denominator. That means the more massive an object is, the smaller that wavelength is. We can actually use electrons as microscopes because we can diffract off of their matter waves. Their matter waves are so large, we can actually use them. However, more massive objects have much larger momentum. And remember, that thing in the top is Planck's constant. So it's really easy to shrink it down. And even our own bodies have a matter wave, but they're too small to observe. The biggest lie you'll hear is that entanglement allows faster than the speed of light communication. That's not true. And there are a good number of videos and sources that point this out, but they usually don't explain why, at least not in an easy to understand way. But here's the simplest explanation for why they cannot communicate faster than the speed of light. Let's say we have two observers, Alice on one side and Bob on the other side. Now, they could be separated by a distance of a light year or a couple hundred feet. It doesn't matter. The point is, let's say Alice measures an entangled pair of a particle, like an electron, and let's say she measures it to have spin 1/2. This entangled electron has a partner, like a positron, that has the opposite spin. So when she measures her spin to have 1/2, Bob must measure his particle to have -1/2. That's in the case that the entangled particles came from a spin 0 particle, like a pi meson, that split apart, because spin has to be conserved. So as soon as she measures the spin of the electron, she finds 1/2 and he finds -1/2. He could do the opposite. He could measure his first, and he might find, for his particular case, that his particle has a spin of -1/2, while she finds then that her spin is 1/2. The point is, the spins always have to equal 0 because the entangled angular momentum, the net angular momentum of the system is 0, and that's conserved. Here's the part that controls whether or not she can do it faster than the speed of light. If she could control her measurement and guarantee that her particle was measured to be -1/2 and control that, then she could decide when to do the measurement, and she could time it, and she could transmit her information faster than the speed of light potentially. But she cannot do that, and he cannot either. If one person makes the measurement first, the other person has no way of knowing that that person made the measurement and that there should be a value associated. If they could control that, then he could know even before he made the measurement what the result was. But since he has no way of talking to Alice when she's separated at some given distance, he has no way of knowing the result of her measurement, and she can't control that result. So she can't say, I will definitely measure the spin to be -1/2 at this time, and I can guarantee that. If she could, then they could communicate faster than the speed of light. All right, enjoy this latest clip from my brand new documentary on dark matter, out now on YouTube. Click the link in my bio and watch the full thing. It's an hour long. I promise you will love it. So what you're looking at here is line of sight views of photons that I would see from gamma ray emission. But how do I actually get these sky maps, which is the galactic view of all the light coming from different angles? I'll show you how I do that right now in simulations. In order to get an accurate picture of what our telescopes observe, I have to orient myself in the center of the galaxy 8 kiloparsecs away. So I do that here with this line of code. I take a coordinate transformation and I transform into spherical polar coordinates using these lines of code. And then I actually select a distance that I want to orient myself from the center along the x-axis, which in this case, this d variable will be 8.3 kiloparsecs. And that positions me at the right location where we're actually located in the Milky Way.